Starting recording, and let me introduce Professor Herbert Edelsbrunner from Institute of Science and Technology, Austria, who will talk about fluid density fingerprint of a periodic set. Please, Herbert.
Thank you, Vitaly, for the introduction and also for the invitation for this meeting. I think my talk is mostly a service talk, namely I need to introduce various definitions and concepts for the next two talks, which are given by two of my co-authors. So this paper is by Phil Smith and Theresa Heiss, next two talks. Also Matthijs Windreken, who works at ISD also, and with Vitaly Kurlin. And this is about the density fingerprint of a periodic set. Okay, so after some background, I'm gonna state what the goal is of this whole enterprise. And then I introduce some more geometric concepts that explain things. First order, which are more classical, like Voronoi and Delaunay tessellations. And then I go to higher order, which are less well known. So here is a Delaunay set. It's a really infinite set in 2 dimensions. Actually, maybe you should think in 3 dimensions. My drawings are all 2-dimensional, but all the writing is 3-dimensional. But it's locally finite. And for such a set, we define the packing radius, which is the half of the smallest distance between 2 points. And it's called a packing radius because you could put a disk of this radius around each point, then those disks do not overlap. They form a packing. And big R, which is always larger than little r, is the covering radius. It's kind of the disk that you can, the biggest disk that you can fit in a hole between the points. And it's called covering radius because if I put such a disk around every point that I have, then I cover the entire plane or 3-dimensional space if it's spheres and balls. And such a thing is sometimes called an RR system. And then a Delaunay set is an RR system where the little r is strictly larger than 0 and the big R is strictly smaller than infinity. Okay, so this is not necessarily periodic, but somehow modeling something like a well distribution in space. And the particular case are the lattices. So a lattice would be given by 2 vectors. I call them EI, E1 and E2, 3 in 3 dimensions. And it's the collection of all integer linear combinations of these 2 vectors. So usually the vector in the middle, that'll be the 0, and then you have this whole collection of vectors. So this is a lattice. If I look at the parallelogram spanned by the 2 basis vectors, we call this the unit cell. And its volume in particular is very interesting because I can tile the entire plane or space with copies of this unit cell. So this volume is characteristic for the lattice. A motif is a finite set inside of the unit cell. And then I copy it into every unit cell that I used for the tiling, and then I have a periodic set. So this is this motif M, Minkowski sum with the lattice lambda. And I use this notation all the time. So lambda is for lattice, U is for unit cell, M is for motif, and A is for the periodic set. And the most important concept today is the periodic set, which brings me to why we do this work. Namely, our goal is to define a fingerprint for crystals or crystal structures. And a crystal structure we model as an isometry class of a periodic set. So this is a periodic set together with all translations, all rotations, and also reflections. And we would like to map such an isometry class to a fingerprint, which is some kind of structure. And we would like to have this map by Lipschitz, which means it's stable in both directions and also complete. So let me get to the conditions. So this is a function of the fingerprint, and I will introduce a fingerprint that we hope satisfies all the requirements that we have, but at the moment we are short of proving the third one, except in special cases. Okay, so the three requirements for the fingerprint are invariant under isometries of three-dimensional space. This is actually redundant because the way I define the fingerprint is for the isometry class, but somehow it's very natural to think of the fingerprint of a particular periodic set, and therefore we usually state that it's invariant under isometries, which it has to be if it's for a class. Second thing is it should be stable under perturbations. That'll be the contents of the third talk today by Theresa Heiss, so I won't say much more about it. And it should be complete, by which we mean that any two different periodic sets should have different fingerprints. So the function should be injective, but we can't prove it at the moment. We can prove it for the special case when the sets are in general position. And we don't have counterexamples, so we are hopeful. Hope dies last. The second talk by Phil Smith is about how to compute these things. So I also will not say too much about computing, but I will introduce the structures that are necessary to explain how this works. All right. Now some concepts that we need here. First order concepts. So this should all be still familiar to you, I hope. I draw a lattice for simplicity, but you can replace a periodic set for it. But I start with a lattice. So the Voronoi domain of a lattice is, of a point in a lattice, is a set of points where this point A is the closest. So in the plane, it's typically a hexagon, like so. And then I can copy this hexagon everywhere, so the Voronoi domain, to tile the entire plane in this case. That's for the lattice. If you have a periodic set, you would have a different Voronoi domain for each point in the periodic set. But then if you go to another fundamental domain, everything gets copied. So instead of just one polytope, you have several, but a finite number, and they get copied to tile everything. Now, some properties about this Voronoi domain is, first of all, the domain of another point B is just the domain of A translated from A to B. And you see this in the picture very clearly. The volume of a Voronoi domain is the same as the volume of the fundamental domain. And this should also be obvious because we have one domain for each point, and all the points are the same. We also have one fundamental domain for each point, and they're all the same. So since they both cover without overlap the three-dimensional space, they should have the same volume. And typically, the Voronoi domain in the plane of a point would be a hexagon. And non-typically, it could also be a rectangle, like so. So I just deleted every other row, and then I have a rectangle. In a plane, this is a very simple situation. In 3 dimensions, there's 5 different types. that we probably don't have to get into now. So like BCC lattice, FCC lattice, prism, cube, and there's an elongated version of the FCC fundamental Voronoi domain. All right, let's move on to density. Since the fingerprint that I want to introduce, we call the density fingerprint. And here is how it goes. When I have my lattice, I grow a ball of radius t around it. I use t because the little r is already for the backing radius. So I use t consistently for the radius. So every point gets a ball of radius t. And then we introduce this function phi of t, which is the probability that a random point lies inside of at least one of these balls. In the case of a lattice, everywhere looks the same. So it's enough to, instead of looking at a random point in the plane, to look at a random point inside of a Voronoi domain. Let's take a random point in this rectangle. Then the probability that the point is inside at least one of the disks is the same as it's inside of the disk of the point that defines this Voronoi domain. And so I shaded the part of this disk that's inside of the rectangle, and then so the probability is the volume of this shaded part, namely the rectangle intersected with the disk, over the volume of the rectangle. Okay, so this is a simple formula. And you can imagine as t grows, so when t is small, the entire disk will be in the rectangle, like so. And therefore, in this case, we just take the volume of the ball divided by the volume of the Voronoi domain. And then it grows, so it starts to interact with the boundary. It leaks out a little bit until it covers the entire domain. When it covers the entire domain, you'll recognize this radius as the covering radius. So if t is larger than the covering radius, then of course the probability is 1 because everything is covered, so the point cannot escape lying inside the balls. So this is just a little case analysis. So we see that most of the action is when a disk starts to intersect the boundary and part of it is inside and part of it is outside. That's when the interesting stuff happens. And to capture something about this interesting case, we go to higher order versions of the concepts. And by higher order, I mean, instead of looking only at the nearest point or at one disk, we look at the k nearest points or the k nearest point or k disks or k balls. Okay, so k will be the parameter that generalizes first order to kth order or higher order. So I'm using the name of Brillouin zone here. I'm a little suspicious that maybe the meaning in which I use it is a little bit different from the classical way crystallographists think about it. But you tell me afterwards. So bear with me right now and let's just go through the definitions. First step I'll take is I generalize the first order Voronoi domain, or just Voronoi domain from earlier, to the kth Voronoi domain. And a kth Voronoi domain is a set of all points x, such that k minus 1 of the other points can be closer than my point A, but not more. Okay, so here in my picture, I have k equal to 2. So the point in the middle, that's my point A. The rectangle around this is where A is the closest to the point x. And then if x is in these wings outside of the rectangle, that's when A is the second closest. Okay. So because this is for a lattice, so if I look at the kth Voronoi domain of another point B, all I do is I take the one for A and translate it. And the volume of this kth order domain is K times the volume of the fundamental domain. And I thought I'm gonna make a little drawing to illustrate why this should be the case, by introducing what I call the kth Brillouin zone. So this is very similar to the kth Voronoi domain, except that I subtract the K minus first Voronoi domain. So I remove this rectangle in the middle. So this would be here the second Brillouin zone. If a point X is inside of this second Brillouin zone, then A, the point in the middle, is the second nearest. And that's all there is. So it's like a ring of regions around the first Voronoi domain. And then if K gets larger, the rings get larger. And they become somehow a thickened sphere around the point in a limit. Okay, so here we see the second Brillouin zone. Now let me copy or draw over it the second Brillouin zone of the neighbors, up and down, left and right. And you see that some of the wings of those extra Brillouin zones cover exactly the rectangle inside. Makes total sense because inside of this rectangle, A is the closest. So somebody else must be second closest, either the left or right or up or down point. And so the left, right, up and down point, they divide up the real estate of A into 4 pieces in this case. And I could repeat this construction. So I could put all of them in, and then so they again cover the entire plane exactly once without overlap. So this proves that the second Brillouin zone, or in general the kth Brillouin zone, has volume exactly equal to the volume of the fundamental domain. And that's also why earlier I said the kth Voronoi domain has volume K times the volume of the fundamental domain. All right. Good. And then we come to the definition, which is the critical definition for the next talks, namely the density fingerprint. So phi sub k now is the probability that the point lies in at least k of the balls, where I draw a ball of radius t around each point. And then we generalize just from the earlier thing. We notice that this is also, I can just look at the point inside of the Brillouin zone, the kth Brillouin zone, intersect the ball with the kth Brillouin zone, and divide by the volume of the kth Brillouin zone, or the volume of the fundamental domain. It's the same thing. And now we claim that this is really the probability that at least k of the balls contain the point. A brief argument of why this should be true, if it's not already obvious. If a point is in the shaded part of my ball, so this means that the point in the middle, A, is the k nearest. Since it's inside the ball, and the k nearest, so the k nearest has distance less than t. So therefore, the point is in at least k balls. If it's outside of this ball, but in a kth Brillouin zone, then that means the k nearest has distance larger than t. So it is covered by fewer than k balls. All right. So this gives a simple way of, or a convenient way. Let's say convenient, because simple is maybe a little bit different, because it's still tricky, and Phil will tell you more about how he deals with the tricky situations. But in any case, so this is the probability, and the densities that we look at are actually the differences. So psi sub k is the probability that the point lies in at least k points minus the probability it lies in at least k plus 1 points. So therefore it lies in exactly k points, in exactly k balls, at least k and not k plus 1. So this is the kth density function, and then a density fingerprint is all these functions lined up, psi1, psi2, and so on. So these are all functions, and I thought the last few minutes I spent by showing some examples of how these things look. And maybe the examples are sufficient if you got lost in the details somewhere. I hope not. Okay, here is a simple lattice, the square lattice. And the blue disk, I'm going to grow it. And now it overlaps, the disks overlap even more. And now they overlap a lot. The blue is gone, so this means now we don't see any point inside of the only one disk anymore. All right, so this is my point set. Here are the density functions lined up, the first 8 of them. So what do we look at here? From left to right, the radius increases, and from bottom to top, the probability increases from 0 to 1. So let's see, what do we see here? For example, the second function starts around 0.5. That means until 0.5, a point can only lie in one disk. So 0.5 is the pack-in radius. That makes sense. And then something happened at 0.7 when the region of 3 and 4 start. But my personal favorite is a slightly different way of drawing the functions. Namely, instead of drawing them next, we keep adding them. So I take the first function, and then I take the first plus the second, and the first 2 plus the third, and so on. So then I get this drawing. So you might recognize the first function is the same, but the second one somehow moves up. And I can see a little bit more here, I think, because before the second function starts, the first function is a quadratic because there's no overlap. It's just how the ball grows. I mean, it's quadratic because we're in a plane, so how the disk grows. And what's interesting also is then when the first and second hit 1. So this means that I can cover the entire plane by just having pairwise overlaps. And then when 3 start to overlap, 4 also start to overlap. This is just because of the square grid structure. We call this a densigram. I think it's kind of nice pictures. Maybe somehow we should make window frames out of it, or windows, church windows. That's the thing. Okay, one other example here is the hexagonal grid. Growing the disks. Again, you see when the white little triangles disappear, I can cover the entire plane by just pairwise overlaps. So this is my sequence of functions, and here's my densigram. Starts quadratically, and again up here, when the first and the second hit 1, the third did not enter yet. But now there's triple, since the third function is fairly substantial. So the triple overlaps occur much earlier than the 4 tuple overlaps. Only 5 and 6 start together with 7. So this tells you somehow a little bit about the structure of the point set. And this is all I wanted to say.
Thank you, Herbert. Let's clap for Herbert, please. Exactly on time. Thank you very much. Questions for Herbert, please. Herbert, are you here? Can you hear us?
I can hear you, yeah. I'm trying to get my slides off the shared part, but I'm not successful so far.
Okay.
I have a question.
Okay.
Please.
I just wonder, it's not a substantial question, but why do you start with the first function rather than the zeros?
You can see the zero function. It's the white area.
You can see that, but you can already read off a lot from the zeros one, and then you don't even have to get to the first one. So it's just from the point of view of presentation, it is nicer because.
But it's right. It's right there.
Is it? What do you mean?
Well, if you go in a densigram.
Yeah.
The white area to the left of where the first function starts, that's the zero function.
Yeah, but in the official fingerprint, because I think that the idea is that you can say that if you look at the first function or the first two functions or the first three functions, then they already hopefully determine the configuration, right?
Yeah.
But already the zeros determines a lot. And on the surface of it, you know the zeros if you know all the others. That's like using all the others. So I think that mathematically it would be a little bit nicer, but of course there is no substantial difference.
Thank you, Janusz. Any more questions for Herbert? Okay, so the next two talks by Phil and Teresa will explain more details of this density fingerprint. Phil, could you try sharing your slides again?
Yeah, I still don't have the desktop.
Still struggling. Okay, so one option would be, so since I have your slides, I could show the slides and run over them. And can everyone see the slides by Phil?
Yes.
Okay. So the slides visible and in full screen mode now, right? So I could, yeah, I could run the slides, and in that case, Phil. So I need your hints when to move next. So you could. So let me actually let me for a moment stop